Hey everybody, I want to show some first uses of R and RStudio here to focus on bringing in data and turning them into objects we can work with in R, and also visualizing them with graphics. So first, let me show how it is and what the basic syntax is like for bringing data in to your computer. For our class, oftentimes the data sets are going to be ones that you will download from the website that goes with the textbook. So if you were going to try to bring in data from a website, then the syntax works like this. You name this object, this thing I'm going to call fish, and then you use this command read.csv. That's basically saying that you're going to read a spreadsheet file in a particular format. Your text tends to use what are called CSV or comma delimited files. Whenever you make files, I would recommend saving them in that format too. But anyway, within that read CSV command, there would be, you have to then make what's called an argument. So you say next, you're going to be reading from a URL, and then another nested parenthesis within that, and then quotes the URL that you're coming from. So if you want to run this command, you put the cursor on that line, and you can either press the run button up here, or you can hit on the Mac, it's Command Enter. It's probably Control Enter on the PC. But I run that, and that shoots that command down to the console. And you'll notice that there's also now this object in here that I called fish. So it's a whole zillion observations from two different variables. When you get to this point, you have a couple options for what you can do. You can, if you press this little button that kind of looks like a little baby spreadsheet, click that, it will show it in the script window up here. So this is what the raw source would look like. So it's got two columns, and if I kind of scroll down, it looks like all wild survived. I'll scroll down a bunch. Hatchery survived, wild not caught. So this is what the raw observations are like. But it's really hard for us to visualize what's happening with raw data, so we're going to make some tables out of this as well. So anyway, the other way to be able to visualize, so you notice when I click that little button, down here in the console, it actually sent a command. And if you just wrote fish, if you wrote fish down here in the console, what you then get is like showing what the actual data file looks like. But you'll notice at the very bottom, it kind of will overflow at a certain point. So it'll show about 500 lines of most kinds of text. Another way to be able to do this is if you use the command called head. I'm just going to type this into the console. You do that, and it'll show you the first few lines, just so you can kind of see what you're looking at. But watch me do this again. There's something to notice. I type HEA. By the time you get 3 letters in, RStudio will suggest different commands. So it actually is helpful not to type too fast, whether you're in the console or in the script window, because RStudio wants to help you out. And similarly, so that's the command, and then you direct it towards something. So I start typing fish, which is what's in there. And now it's suggesting, one of the things it suggests here I can put in is this object that I've already made called fish. You notice there's a test called a Fisher test that we'll do another time, but you can ignore that for right now. So let R help you out if you're trying to do that. I just sent that same command again just to give you a sense of that's how it would work. So even though you're seeing the fully cooked versions up in the script window, typing them in yourself, the interface will actually give you some hints along. So that's one way to be able to do it. Another way that you're going to want to be able to bring data in is if it's downloaded onto your computer. Now, there are a couple things you should know. You can, if you go up to the session window here, you can specify your working directory. You can make that a file, say just for this, like a folder that's just for this class, or you can make it your desktop, or you can just leave it alone. There are different ways to do it, and when you're doing things that are more complicated than just problems for a class, setting your working directory actually makes some sense, but it's probably not critical right now. But if I want to find a particular file, I use this command called file.choose, and then I leave the parentheses where the argument would go. I leave that empty. So when I run that, it opens up a dialog box. So here, this is going to have me navigate over to wherever my data are stored. So I'm just going to go on my particular computer over to the public files, and I'm going to download this SkullByte data set. I click open, and notice here in the console, you get a 1, which is basically R telling you this is feedback. And then in quotes, this is the path that leads, like the folder structure that leads to that particular file. So then what you do is you then copy that whole path, which is what I did up here, and then that would do the same thing. In this case, I'm making an object I'm going to call SkullByte and use this left arrow. Then the command is read.csv, like what I used up here before. Read CSV, and then the parentheses come, and then quotes. In quotes, that whole folder structure to get there. Hit run. Now there's a second object in here called SkullByte. Now, that only works for me because I'm coming from my computer. On the other hand, if you're going to download this if you want to get the same file from a website, you can. You can just go to this Dropbox link. If I click this now, it would just make SkullByte again. But if you want this file to be able to play with it later, this is the command you should use. Okay? So that's 2 ways. And the third way to be able to get data into your R session is to use some of the built-in data sets that R has. Now, if you just do this data command without any argument in there, and then hit return, or you can hit the command return or the run button, this gives you a list of all the data sets that are like preloaded. If you want to browse them, you can, but for right now, I'm going to get out of that. But I can specify here, I'm going to open up this data set that's looking at like water levels of Lake Huron. So I click, so I just type in data, then in parentheses, then in quotes, Lake Huron, and then run that. And that will make this thing now that's calling a value. This promise means it's still kind of downloading it. It'll fill in a minute. This value is actually a whole bunch of different lines and arguments. But if you want to see what it looks like, you can just type in the name of that value, Lake Huron. So I run that, and it'll give you what this vector looks like. So it's specifying here it's a time series. So there's other information that's kind of wrapped around it besides just like like just a spreadsheet. So anyway, those are 3 ways that we are commonly going to be bringing data in. I'm either going to use stuff that's coming through Whitlock and Schluterbook, or files that I will host, or the built-in data sets for R. Okay, so this kind of big mess of a file isn't super helpful. Now, what I'm going to do is just a little bit of a demo of like how you make tables. So if I want to let me just see here. If I go to SkullByte and then I view it, you'll see I have a little spreadsheet here that has a bunch of species of living carnivorous mammals, the family that each belongs to, the length of the skull in centimeters, and then what the bite force is in newtons. This came from literature from a project I did with the student Bailey Dameron last year. Now, if I want to be able to work with these, then it's like rather than just view like having this whole thing, if you want to actually make a table out of these, I'm going to make this object I'm going to call family table. You don't have to capitalize the T in the middle, but if you do, you have to remember to continue to type it that way because R is picky. It is like case sensitive. So, I'll usually put in capitals in the middle of words for like table or regression or something like that, but I don't do it like all the time. And I use this kind of setup here where I go sort, then table, and then SkullByte $family. What that means is, here, let me show you this in the console. If I start typing, SKL, again, 3 letters in, it'll say, all right, it's suggesting SkullByte. So I'll hit return and that'll fill in the rest. Then I put in this $. Notice that once that $sign goes in, it suggests each of the 4 columns that you have in your data set. So you can then select which one you want. So in this case, I'm going to use the family. I'm not going to fill in the rest of that because I'm going to use this filled in command. But that's the thing I do a lot. If I just want a particular column, I will sort of let R sort of help me out. Anyway, I run this command, and it makes this new value that is called family table, but it doesn't like show it to you. If you want to actually see what it looks like, you again have to type the name of the object. So I'm going to run this, and then it'll show you, here's this list. So I have 5 canids, 5 cats, 5 vivarids, 4 mustelids, etc. Now that's okay, but that's not exactly a frequency table. So what you can do is basically you can do this data frame command, again, where you specify the frequency is you add the margins, what they call the marginal totals, from that object you already made, and that will make a vertical table that also sums things up. And notice it also kind of sorts them. This sort argument I put up at the front here, that makes it so whatever happens most frequently shows up at the top, and the least frequent outcome is there at the bottom. Okay, so now we know that there are different ways to be able to express what these, if you want to show what the distribution is like of the families in my sample. So if I have a categorical, like nominal scale variable that I want to show counts of, I would use a bar plot for that. So the syntax here is easy. It's just bar plot, and then in the parentheses, the argument family table. So when I do that, I get this, missed the target. I get this figure down here. Now this looks okay. You'll notice it's missing a couple of the family names. If you click on zoom, that'll actually help to make it a little bit better. So you can, that kind of spreads everything out optimally. Or if you were going to push this into a document, you could also use this export button, save as image. Again, I like EPS. And then I'm going to move this a little bit. You can then grab the corner here, and you can spread it out as wide as you want, and it'll kind of reset it. So that's something to do if you want to be able to download it. Then you'll be able to read everything. I'm going to cancel. Or you can do it like a slightly prettier version by running this. Notice it changed a couple things. Oh, by the way, this is something you should know. If you go down here into the plot window, if you go back like this, you notice it shows the previous plot, and then forward shows the one where you have now. Let's unpack this a little bit. So here to this bar plot, it was the same thing as the hashtag basic version of, I said I'm going to work on the family table, then I put it on a comma, and then I say make the Y label, in quotes, frequency. So that's down here. Las equals 2. This is an argument that 2 is like a positional argument. So notice it went from the family names going horizontally to going vertically. There's a 3 and a 4 as well, as you'd expect, but this 1 or 2 is one of the kind of most helpful ones. And color equals firebrick. I always use firebrick because this is what your book uses, but it's that reddish color. If I wanted to change this to something else, actually, here's another thing you should know. I go down here to the console. If I go to press the up arrow, then it will put in whatever the previous command was. Or I do it again, it does the previous command that, again, etc. So if I want to change one thing, let's say I want to change, I don't want to do this as firebrick anymore, I like green, so I'm just going to do this in some color of green. Then you'll get, that's a hell of a green. Let's change this to green 3. Nice. Then that's one way to kind of change that. You should do this with R. You should, when you have a command that works, you just want to kind of see what happens if you change things around, go ahead and do that. You're not going to break anything. See that last one that made stuff go horizontal again. Or I'll change this to 3. It does the same thing. It's not as exciting as I thought. Let's see what 4 does. No. Okay, so 4 is outside the parameter. So this is what an error looks like. I'm going to try not to have a lot of these in the videos I make, but just so if it happens, that's okay. Again, you didn't break anything. You just kind of go back a couple ways. You can either just go back and say, all right, this is the last graph I had that looked good, or I can go pink, kind of up arrowing through there till I get back to the last one that I liked. Anyway, that's what a bar chart looks like. So notice it has frequency on the y-axis, and there are spaces between each of these nominal scale variables. So that's what I have for a bar chart. Related to a bar chart, but not the same thing as one, is a histogram, where we're comparing, we're looking at the frequencies of different ratio scale continuous variables. And If I want to run this, I'll just kind of shoot this to run. What the basic command gives you is you do this, the command is hist, and the argument is, again, skull byte, but I use the $, and I specify that I'm using the byte column here. Right equals false refers to basically, is there an endpoint? Is there like a solid like right side to each of your bins? In this case, there isn't. And so this is what what it basically looks like. They are, it's again black and white, but you notice there's like no space between the bins here. Also, notice what the defaults do here. This default x-axis label is just whatever we call the name of that column. And there's like a main title as well. But like in real life, you like hardly ever need that in a document because you're going to have a legend to your document. You don't need like a title on it. So let's do like a slightly nicer version of it here. Oops. Oh, I just hit return instead of command return. But actually, it's a good thing to remind me to tell you. If I hit, let me just undo a couple. Okay. One thing that R doesn't care about is how many returns you have. So for example, if I put a return here, notice it'll kind of indent it a little bit, but it doesn't stop reading the command until it gets to like wherever the end of the parenthesis is. So if I just run this command, if I'm on like the first, second, or third line, either way it'll observe that whole command. So here, again, this looks a little bit funny just because the way the spacing works. If I hit the zoom, it looks pretty normal. What you see is there are like some additional commands. There's the same basic one as had above. Here I specify that the X label will be byte force in newtons. The Y label is frequency. This main with parentheses with nothing in it, that means that it's basically they'll have a blank title. So if I go back to the basic one, you see it had like this kind of janky title on the top here. But if you go forward here, you see we don't see that anymore. Y limit, this is we're going to go from 0 to 20. So that's 0 here up to 20 there. I made the color fire brick again because why not? And then also I did this for the breaks. I had it go from along the x-axis. I had it go from 0 to 1500. The first I did from 0 to 1500 by 100s. But I can also have it go by 50s as well. And that specifies what my bin size is. So compare the difference. You go left and right here. You notice here, this sort of is putting it out as in hundreds, 0 to 100, to 2 to 3 to 4 to 500, 6 to 7 to 8, 9 to 1,000, etc. Whereas here, it's doing it every 50. And how many bins you choose depends on the kind of signal that you want to send. But anyway, that's the basic way to be able to run histograms and like play with this. You'll notice that we'll have there'll be like a lot of junk that'll like accumulate in your console. That's like okay, that'll happen as you're working with as you're working in R. You can save it or not save it. Eventually, you run out of buffer space. Like if I scroll all the way up to the top. No, it does, and I haven't done so much that I lose like the very top of it, but the buffer in the console will eventually run out of lines. But that's okay, because if you really wanted to go back to see what else you've done, all this stuff is also in the history. Anyway, scatterplots. Now, scatterplots are like the basic way the command is plot, and then the argument is laid out in sort of a y tilde x. So I use the byte column, then the tilde, the little squiggly line, at least on the Mac that's next to the 1, and then comparing it to the length. So if I run this one, I get a scatterplot that looks okay, but again, it's kind of basic looking. If we put in some additional commands here, we can make a pretty nice looking version. If we go to compare left to right, there are a couple things you'll notice. First of all, of course, I made the color fire brick. I updated what the X and Y labels were. This BTY equals L. Look down at the shape of this. See how there's like a whole box that goes around this graph, if I go to the newer one, it's like in the shape of an L. It shows like the X and Y axis, but doesn't fill in the rest of the box there. There are different commands you can do to get, depending on whatever sort of shape you want your graph to have. Another thing that it did, this PCH argument, it went from being the default, which is open little circles like this, to here, PCH 16. That's a command basically that says make the symbol or a filled in circle and one that's red because of the color I defined. And also, if you look back and forth, you notice how like the default one's like a little bit smaller than the one that I have here. That's because of this thing, the CEX equals 1.5. That makes the icons like 50% bigger than before. I'll show you another way. So if I change the CEX, if we made that, I don't know, 3, then the icons get even bigger and frankly kind of goofy looking, so I don't love that. Up arrow again, put this back to 1.5. But you don't have to have them be filled in circles. There's a whole, you're going to use filled in dots like the majority of the time, but there are lots of kinds of icons that you can use. If I just change it to 4, let's see what I get. Okay, at X's. So there are by playing with each of these little arguments, you'll see there are different kinds of things that you can, different kinds of outcomes you can get. So anyway, I'll load up later on kind of shortcuts for what all these abbreviations are and everything, because I think that will be handy to have while you're working with this, so you don't have to go back to a script or a video or anything. Anyway, so that's if you're trying to look for relationships between two different numerical continuous variables, in this case byte force and skull length, then this is a reasonable way to be able to represent it. Let's see, if we zoomed this, oh yeah, I guess you can like this. It is possible to be able to squish this to make it fit for whatever you want to have your graph look like, but some of that's going to depend on like the kind of space that you're fitting it in. This is both for this plot zoom command as well as if you're exporting the image. Okay, just a couple more ways to do graphs. For line graphs, I'm going to load in that Lake Huron. I would load in that Lake Huron data set, but it's already in, so I'm not going to redo that. A line graph, it's pretty simple. It looks just like the same plot command that you'd use for doing a scatter plot. But in this case, you do type equals L in quotes. That means line graph. All right. So if I run that, this is showing the zigzag line. There's each of the points of each of those observations by year. And again, there's like a prettier version that you can make of it. I didn't change the color or anything, but the prettier version will have better labels here on the axes. A strip chart is something that you might not be as familiar with, but it's actually kind of a handy way. Strip charts and box plots are both helpful for looking at distributions of like observations within, like numerical observations within categories. So let me show you. I'm going to load in another data set here. It's going to be chicken weights, which sounds adorable. And if you view it, what you'll see is this is a few observations of, look here, 71 observations of weights of chickens that are raised on different kinds of feed. All right. So now what a strip chart does is it looks like this. Let me zoom it. It shows each of the individual outcomes here, and how they're just distributed. I personally like the default icon here because if you have a bunch of observations that like kind of overlap each other, you can see that a little bit more easily. And this was there's an argument here where it says method equals jitter. That's what makes them kind of spread around a little bit. Let me just resend that command. But if I get rid of that jitter argument within that, Notice how they all line up straight on top of each other. That like looks okay, but actually I sort of like this better because I think that's better for given the impression of variability within your sample. And then there's like a prettier, I made another strip chart here for the carnivore data that I have. I don't love this as much just because it's not quite as data dense as the chicken weights one is. But again, this is when you have categorical, like categories, but they have numerical observations within those. So in this case, you see a lot of the canids have relatively low bite forces, but so the felids are actually quite spread out. So the like your lions and tigers, they're way up here, much higher than the rest of the carnivores in my sample. Anyway, the last kind of plot I want to show you is a box plot, which again I think are super useful. Using the same skull bite data, you can make it look like this. So this is again showing each of the families. I'll zoom it. Each of the families and what the distribution of points are like. But this is now showing you your interquartile distance, right? So this line in a box plot, you remember from the module before, this is the median, not the mean, but like the 50% line. And then from here, this part of the box, to that part of the box, this is the 25th percentile. Up here is the 75th percentile. So 50% of your observations go in here. The rest of those observations, so the box shows you the middle interquartile range. And then the whiskers on the top and the bottom, those show you the rest of the distribution. But it's like here for the canids, this observation here is like far outside the rest of those observations, so we'd call that an outlier. There's another little outlier over here. Anyway, you can make a slightly prettier version of this if you like as well, where I kind of rotated the I rotated the taxon names. But even with that, notice it doesn't totally show it all. Yeah, so sometimes you see this is like lost down at the bottom. You gotta kind of watch out for that. I think when you export this, it'll probably be okay, but you can make those. There's an argument you can do to make those smaller. Or for just kind of run the same thing, but for the chicken weights, we get a very similar kind of graph here. But again, it looks like if you're looking in the little pane here for the plots, if it looks like you've like lost some of your labels, again, if you zoom it, you'll see that they're still there. It just depends on like the size of your window. That's the basic stuff I wanted to show you. I know it's kind of a lot of talking, but what I really recommend you do is now download that script that I wrote, that M1 visualization script, and you can kind of click through here to do the same processes. When you also download the script that goes with the Whitlock and Schluter text, then you can see actually recreate how they made the texts the figures that are in their text. Anyway,